This video is the second in the series on bonding. In this one we will be talking about covalent bonding. A covalent bond is a bond that's formed by sharing a pair of electrons. So every covalent bond has two electrons. When we hold atoms together in this way, we call them molecules. So a compound is molecular if it's held together by covalent bondings. When we have ionic bonded compounds, those are not referred to as molecules. Just as we were using the octet rule with ionic bonding, this also comes in useful with covalent bonding. And remember, the octet rule is the rule saying that most atoms, not all, want to have 8 valence electrons to be most stable. Uh, there are exceptions to the octet rule. Again, that's just most. For example, hydrogen is one that we'll really have to pay attention to. Hydrogen only ever wants 2 electrons because it only uses that first energy level, and the first energy level can only hold 2 electrons. So here we have some different examples of atoms. Right now we have, up in the top left, we have a hydrogen here with just 1 electron. And again, it would want 2 to have a full valence shell. And then we have a fluorine that has 7 and would want 1 additional electron to have a full valence shell. Now, under ionic bonding, we would just take hydrogen's electron and put it over with fluorine, and hydrogen would become positively charged and fluorine would become negatively charged. The only problem with doing this is both hydrogen and fluorine have fairly strong holds on these electrons, and neither one of them can take the electron away from the other. So the only way for both of them to be stable or happy, if you will, is for them to share these electrons. So we oftentimes can illustrate this by drawing in a circle to kind of represent that. In this case, oh, hold on, I need a circle. There we go. So draw in a circle those two to show that those two are shared. So now if we look at it from hydrogen's perspective, it has 1, 2 electrons, so it has a full valence shell. For fluorine, it has 1, 2, 3, 4, 5, 6, 7, 8 electrons, so it has a full valence shell. This sharing can happen between more than just 2 atoms. If I have an oxygen atom, and I'm actually just realizing that I forgot to draw in all chlorines, we'll take care of that. So an oxygen atom comes normally with 6 electrons, and a chlorine atom comes normally with 7, not 1 as I mistakenly drew there, electrons. And again, you can determine this by their placement on the periodic table. Oxygen is in the 6th group, so that gives it, that's how we know it has 6 electrons. Or you could look at its outside electron configuration would be 2s2, 2p4, so a total of 6. Chlorine has a total of 7. Now, neither one of them has a complete valence. Chlorine would like 1 additional to get that 8, whereas oxygen would like 2 additional. If you take and share between the chlorine and oxygen, then that makes this chlorine happy with its 8, 2, 4, 6, 8. And then if you take and share again between this oxygen and chlorine, then the oxygen now has 2, 4, 6, 8, and this other chlorine also has 2, 4, 6, 8. So they both are now behaving the octet rule, and this would be a stable compound, or stable molecule. Not only can this happen between multiple atoms, but we can have multiple bonds in between atoms. So for the example of CO2, 1 carbon and 2 oxygens, we can look at if this carbon were to share twice to make what would be called a double bond between the carbon and the oxygen, that would give this oxygen 2, 4, 6, 8 from its perspective. And then if it also shares twice with this oxygen, that would give this oxygen 2, 4, 6, 8 from its perspective, and the carbon would also have 2, 4, 6, 8 from its perspective. This carbon and this oxygen would be said to be double bonded, and this carbon and this oxygen are also double bonded. In the example of the nitrogen N2 molecule that makes up 70 to 80% of our atmosphere, we have even higher order of bonding. We have a triple bond where in order to, since nitrogen comes with 5 electrons to start with, it needs to share in 3 different places for a triple bond. Now you might think, well, what about like a quadruple bond, or what about other possibilities? As far as I've ever seen, a triple bond is as far as you can go. After that, you start not being able to line up orbitals and things, and we'll get more into that if you go on to the advanced video, how orbitals are actually overlapping to give us these bonding and the different types of bonds that are made. Okay, so we go on now. Now, all of those examples that you saw on the previous slide were all fairly simple covalent molecules or covalent compounds where you can just circle the dots and figure out how the bonding should work. There are many compounds where this is much more difficult to do. You can't just circle dots. And so I wanted to teach you a more kind of step-by-step process that works for everything. And so the steps are all laid out here, and we're going to go through the steps one at a time to talk about what each one means. And as we work through these 4 steps, we're going to be slowly pulling in more things over on the right-hand side. And we're going to be doing this for the compound CH2O, which is commonly known as formaldehyde. Okay? So the first thing you do is you find the total number of valence electrons. And you're going to use the periodic table to do this. So if you look on your periodic table, carbon is in the 4th group, so we'll bring in 4 electrons. Hydrogen's in the 1st group, so brings in 1 valence electron. And oxygen is in the 6th group, so brings in 6 valence electrons. If there is a charge, if you're dealing with a polyatomic ion instead of a molecule, if there's a negative charge, you're going to add 1 for each negative. So if it was 1 negative, you'd add 1. If it was 2 negative, you'd add 2. And you're going to subtract 1 for each positive. And we'll work an example of this one, I think, in class. Okay, so we start off, again, carbon has 4, hydrogen has 1, oxygen has 6. 4 from the carbon plus 2 times 1, because there's 2 hydrogens, plus 6 from the oxygen gives me a total of 12 electrons. The second thing you do is you draw a skeleton structure. You put the least electronegative in the center. Now hydrogen can never go in the center because it can only make 1 bond. And then what you do is you draw in a connection between each atom and the central atom, and then you subtract 2 electrons for each connection that you make. So here you see I put carbon in the middle because between carbon and oxygen, that's the least electronegative. And so it's the most likely to share with multiple things. Then I draw in a bond to each hydrogen. Because I have 3 bonds, I have to take my original 12 electrons and subtract 3 times 2 because there's 2 electrons in every bond. Because remember, a bond, covalent bond is sharing a pair of electrons. So I have 6 electrons remaining. The third step is I take those 6 electrons and I distribute them to the remaining, or distribute them to the rest of the atoms, always starting with the most electronegative. In this case, oxygen is the most electronegative. So an oxygen, since it only has 2 from this bond and it wants 6 more, it will take all of the 6 remaining. Which in the case of hydrogen, that's fine because hydrogen only wants 2 and there's 2 electrons in this bond, and so it has the 2 that it wants. It's happy. The problem is carbon only has 2, 4, 6. Okay, so now what you do is you pull in lone pairs as necessary. Since, like I said before, carbon is not happy, I need to borrow some more electrons from the oxygen to give carbon its octet. So I take the electrons and boom, put them in, bring them in with the carbon, and there we have it. Now the carbon has 2, 4, 6, 8. Again, each line stands in for 2 electrons. Oxygen has 2, 4, 6, 8 because those 2 purple ones over here are in this bond. Hydrogen has 2 and this hydrogen has 2. And so this is our overall structure of the atom, or sorry, of the atom, of the molecule. When we're naming covalent compounds, we have to be very specific about how it is we name them. The thing with the covalent compounds is you can have multiple ways of combining two elements. You could put one with one with two, two with four, and so on. There's many different ways to do this. And so when we're naming them, we have to be very specific. This is different from ionic. When you have two ions, once you know the charges of those ions, there's only one way to put them together that's going to make the charges balance out. So when we're naming them, the way we name it is with a prefix, that's what this blank stands for, and the name of the first or least electronegative element, and then another prefix, and then the name, or at least the beginning of the name of the most electronegative of the two, and then it ends in "ide." So in some ways they kind of sound like ionic names because they're going to end in "ide" again. The prefixes we use are listed here. So one for mono, two di, three tri, and so on. So these are the prefixes that you're going to need to know for naming and going back and forth between the name and the formula of the compound. It should be pointed out here that mono is only used in the second blank, never in the first. And once we see some example compounds, you'll see that you've actually already known that. Okay. So here's some examples where on the left-hand column I've written some molecular formulas, and on the right-hand column I've written some names. So the first two are ones that you should have already heard of before. There's carbon monoxide and there's carbon dioxide. Now notice I don't say monocarbon monoxide and monocarbon dioxide. I think people just decided that that was just unnecessary. If we look at carbon monoxide versus carbon dioxide, that doesn't seem like a huge difference in the name. And when you look at the formulas, they're not a huge difference. However, one, carbon dioxide is what we readily breathe out as a product of our respiration, whereas carbon monoxide is something if you breathe in, you'd wish you could get it out of your body, but it eventually clogs up all your hemoglobins and essentially suffocates you. So carbon monoxide is one carbon, one oxygen. Oh, now why isn't that? So it's just CO, one carbon, one oxygen. Whereas carbon dioxide is one carbon, two oxygens, so it is CO2. We look at a familiar thing like H2O, and in common everyday speech we call this water, but it can be known by other names. And since there are two hydrogens, we use di, so dihydrogen, one oxygen, monoxide. So water can also be called dihydrogen monoxide. And if you do a Google search for dihydrogen monoxide or DHMO, it's kind of a fun website to visit that gets a petition drawn up trying to get people to agree to get rid of water. Anything sounds, because dihydrogen monoxide sounds a lot scarier than water. If we look at diphosphorus pentoxide and break that apart, diphosphorus, so P2, pentoxide, O5. I keep clicking in the wrong place. So P2O5 would be diphosphorus pentoxide. If I have four phosphoruses, phosphori, I have no idea, and 10 oxygens, it's tetra for 4. Think of like Tetris. If you've ever paid attention to the game of Tetris, every piece has 4 little blocks to it. So Tetris. Tetra, phosphorus, and then 10 for the oxygen, decoxide. Okay. Finally, I is iodine, Cl, chlorine, and there's 5 of them, so pent. Okay, or penta actually. So iodine pentachloride. Okay, so here that's all the skills we'll be working on dealing with covalent molecules. Again, I know one example of doing these Lewis structures probably isn't enough for I would expect to come and master it. We will work on some of these first thing when you come to school tomorrow, because these are some things I think it's helpful to watch somebody kind of work it out live.